going to hear from Max Strickner from the Exploration Company. He's going to be talking about how AM is revolutionizing rocket engine production, so how AM is being used in liquid propellant engines, and some case studies from the Nix Earth and Moon Vehicles projects, and a look, like we had yesterday, on the future of space-based AM for on-demand production and repair. So as soon as you're ready, Max, over to you.
Thank you. Okay, thanks everybody for joining the presentation. My name is Maximilian Strickner, working for the Exploration Company for 2.5 years now. So what the company is actually doing, we're developing space transportation systems. So that is a space capsule that is going from A to B. A usually is a launcher, so a rocket that we travel with, and B is, in our most interesting business case, a space station. So at the moment, all these space stations are actually government-owned and state-owned. This will change, as well as there was a change from private or from government-owned rockets to private rockets, driven by SpaceX, of course. So the same will happen to space stations. The coming space stations, which will be 6 to 8 in the next 10 years, will also be private. And we want to dock to them, deliver a cargo, and take cargo back to Earth in a controlled re-entry. So far, we raised 216 million, or won contracts with these space stations of 770 and our 170 employees in 4 locations: Munich, Bordeaux, Torino, and Houston, Texas, at the moment. So that's how the capsules look. We are developing 2 different modes of the vehicle. On the left, you can see Nix Earth. So that is a capsule that will stay in the Earth's orbit and dock to space stations, bring up to 4 tons to space stations, and take 3 tons back to the Earth. Then we're developing a capsule that should go to the moon. So in the center picture, either to go to the Lunar Gateway, which is a lunar station that should be around the moon's orbit, done by the European Space Agency, ESA, and on the right side, also a moon lander. Biggest difference between these 2 capsules are these little things here. That's 3 rocket engines, liquid methane and liquid oxygen. Some parts of this are 3D printed, for example, the combustion chamber, which you will see later. So first, why do we use additive manufacturing? So we can print very intricate structures. That has been said before. Everybody here knows that. On the left, there's a picture of a quite famous aerospace engine back then, done by Hypergenic and AMCM, which shows what can be done with these technologies. In space, we mostly want to do integrated cooling systems, so that's actually a regenerative cooling. That means that the fuel, which is in our case liquid methane, is not only used in it's not only used for a fuel to propel the vehicle, but also for cooling. So that basically means that you pump through intricate cooling channels your fuel until it reaches the point of combustion, is mixed with your oxidizer, and then ignited to get the combustion going. That increases performance a lot, and in additive manufacturing we can customize material properties. So for these engines, that mostly means to adapt the surface roughness. So if you have higher surface roughness, you have higher pressure drop in the cooling channels, which could be bad, but on the other side also you have enhanced thermal performance due to that increased surface roughness. What basically is happening there is these higher surface roughnesses create microturbulence. These microturbulence lower the pressure, so you have a pressure drop. But on the other side, these turbulences also increase heat transfer. So it's a bit of a trade-off which surface roughness you actually want. So not necessarily the best surface roughness is also best for the application. When you design a rocket engine, usually you have to do a big trade-off between different materials. Classically, it's either copper-based alloys or nickel-based alloys. Copper-based alloys like copper, chrome, zirconium, or GR-COP from NASA are usually used if you have a very high requirement for thermal conductivity, which is the case for rocket engines. The nickel-based alloys are usually used when you have requirements for very high mechanical strength and chemical resistance. For rocket engines, both is the case. So usually if you develop these engines, for example, the combustion chamber, which is the heart, you have to decide between these 2. And that is actually a big trade-off in a thermomechanical way. So you do very big thermomechanical analysis between the materials, and then in the end you would find out which one is the best for your engine. Technologies we're using at the moment is laser powder bed fusion on the right side. So that's, I think, a picture that I took from the very first build shop that we did earlier this year in March. And next year we're also looking into directed energy deposition, DED, for a nozzle extension and for tanks. It's a big project for next year. To get a bit in the applications, we're mostly or exclusively doing space propulsion components. On the left you can see our combustion chamber for the Moonlander engine. That's the third version that we did so far. The first one that we actually printed in-house. So that's, I think, only the second part that we ever did in-house. It's 400 millimeters high, kind of. And here you can actually see this regenerative cooling cycle. So the fuel goes in here, will go into the manifold, collect and be pumped through very small cooling channels through the part to be then injected from the top side and ignited. So the wall thickness of this part is only 4 millimeters, and we have to fit roughly 100 cooling channels inside this entity, which is quite a challenge. So we're really at the edge of the technology here. Injector head is another application that is actually in this view placed on top of the combustion chamber. That's where the fuel, the liquid methane and the liquid oxygen, so the oxidizer, are coming together, being injected in the inside of the combustion chamber, ignited, which then will propel the system. We're also looking into pump systems to actually get the fuel and the oxidizer moving. And in these pump systems, we will develop impeller, inducer, pump housings, motor casing housings, which is also a topic for next year. We did not start that yet. One application example that we did earlier this year is we developed a multifunctional lattice. So in the left picture, you can see an injector head again. It's not ours. That's from a DLR, so German Aerospace Center. And the horizontal copper part that you can see is the faceplate. And the faceplate is the last part between the injection head and the combusting area. So there's a lot of thermal and mechanical load on that surface, which puts a lot of stress on the material. Additionally, we have to print this part faceplate up. So that means you have a complete horizontal surface to support. Additional complexity is this support you cannot access. The entity is completely closed, so we actually have to have an internal support that cannot be removed. That's the first thing we actually also did. We had a lot of cones that would support that surface. In a hot firing test, it actually turned out that there's a heat buildup due to that support. So it was a massive structure, and the heat was concentrating in these cones. The faceplate was getting too high, the faceplate was getting too hot, with the consequence that it would actually melt if we would increase the temperature even more. So what we did is we transferred these cone structures into a lattice structure. So one of our propulsion engineers actually wrote a script in CAD, so an algorithm that transfers these cones into a lattice structure. You can see that applied here. We just printed some slices out of the injector so we could access it. And by the strut thickness of those beams, the angles and the distribution around the faceplate, we could actually adapt the faceplate in a thermal way so that the heat is actually flowing very conformally through the faceplate. And for mechanical, we actually could distribute the stress very evenly over the faceplate. That overall leads to a longer lifetime of the engine. It's just ignited 30 times maximum. So it's actually a low cycle fatigue case that we have here. It does not have to stand a lot of cases, but very high load cases in for a very short time. And that's what that lattice structure is highly contributing to. For validation, it was actually a very quick one. We just printed some samples for traction and compression. So that means we took the actual lattice geometry, so the original beam thickness and the distribution, and we put it to tensile testing. So first traction and then compression, so pushing and pulling, and took some values there. For thermal, we took a representative sample of these lattice structures and checked for turbulence and for velocities compared to reference velocity. And what we detected actually, and that can be seen in this picture, is that we have a heat buildup in the center of the cones. So we still need a little bit of cone here for support in a much reduced way. But what can really be seen is that the temperature is concentrating in the center of the cone, which makes sense. You have a massive structure, so in a steady state, you have then the most heat concentration in the middle, and due to the bad thermal conductivity of nickel-based alloys, there's kind of an inertia for the heat to actually to escape, and that is what we try to minimize with this. So complex products have a lot of challenges, and that's also the case here. One of the biggest challenges is in depowdering. So you can imagine if you take out your part and it's completely filled with metal powder, all the intricate structures, all the cooling channels and the cavities are full of powder, obviously. So how do you get that powder out? Just by using a vacuum does not work because the density of these Inconel powders is too high. You can actually not remove a lot. What we're doing here is partnering up with Solucon, which is a depowdering company based in Augsburg. What these guys are doing is they provide a system where you can clamp your parts, including your build platform, in this machine, and then it would shake and vibrate and turn in a very controlled manner. Actually, they have a software called Pathfinder, and that is analyzing all the internal cavities, all the internal cooling channels, and then creating an algorithm how to best shake and turn the parts to get the powder flowing out. Additionally, you can apply either inert gas or pressured air to that application to finally get all the powder out. It's the most critical step in the post-processing because if one of these cooling channels would be blocked, and the consequence, obviously, the fuel would not flow anymore through it. So the cooling functionality is lost completely. You have a heat buildup, which would, in the end, in a hot firing, lead to a melting of the engine, if not explosion. So that is very, very critical. To check that, at the moment, we're doing a CT scan afterwards to be very sure that we put only flawless parts on the test bench. It's not only about our parts. If a test bench gets damaged or destroyed, that is something you don't want to have in your finance records. Another challenge is space propulsion requirements. Obviously, if you want to fly to space stations and to ISS, that's actually the first one that we target in 2028. The requirements are very high, and you have to comply with standards that they will give to you. And obviously, we have very complex geometries, which really are on the edge of printability for the technology. About testing, the most crucial test is in the end the hot firing. So that happens after all manufacturing tests, and that is usually what qualifies the engine then. What you can see on the picture is the first generation of engine that we printed in 2022, I think. We did that with a partner, but material is the same, Inconel 718. So what happens here basically is you put your parts, so that's a combustion chamber, and on the left, injection head. You cannot really see it, it's frozen from the liquid oxygen. You put the parts on the test bench, and then you fire the parts with a lot of thermocouples and pressure ports. You check what is the temperature and the pressure situation along the part. You then compare if that is the same as you simulated in your simulations before. If there's a difference, this delta will go into the next generation of engines, into the next iteration. And that's basically also the concept how you develop rocket engines. You design, you simulate, you build, you put it on the test bench, and by these values and these measurements that you get, you try to make the best or the next generation of the engine better, and then put it on a test bench again. So that test bench is the qualifying part in the end. Obviously, we also need to do a lot of material testing. So that's a microstructure surface to make sure that the material is complying with the standards and also is able to withstand the thermal and mechanical loads that we have. And then we're looking into subscale demonstrations. What you can see here is actually a subscale demonstration. So the injector head on the left and the combustion chamber on the right are original size, but you also see a flange where the flame is coming out, and here a part is missing. That is the nozzle extension, so basically the last part of the big nozzle That's something that we will do next year. So that's still subscale. And for end of next year, we try to get the full engine for the first time to hot firing. Full size would then be something like 1 meter 20, 1 meter 50, kind of. So the nozzle extension is actually the biggest part. It's not clear yet if that would be metal or 3D printed yet. It's a topic of an ongoing project to find that out, really. For design opportunities in additive manufacturing, we're having a cooperation with Leap 71. There's a lot of parts actually at this trade show from them. They're very active at the moment. So what we do with them is we look into new design possibilities, how to explore new things like algorithmic engineering, generative design, whatever you want to call it, to possibly in the end create engine configurator where you just change a few input parameters like the thrust or the size of the parts that you want to have, to then have a design that is fully designing the part as you want. It's in a very early stage, and at the moment we're doing it with classical CAD, but it's something that we are exploring at the moment. As a technology outlook, we're active in research. We just started a research project with a technical university Munich for laser beam shaping. So that basically means that you take your laser beam and without just keeping it as it is, so a Gaussian dump, a spot that cannot do anything but moving, to shape changing spots for the energy density. So what you can see here on the top right corner is a donut or a ring shape. So that means that you do not anymore have the highest energy density in your center of the spot. That actually opens completely new worlds and new environments for optimization, for speed, for quality, and a lot of other things. Then on the bottom, we're also looking into multi-material processing. We actually got appointed by CNES, the French space agency, to work out a concept for a heavy launcher engine. So the project is called Typhoon, and in the first phase, we're doing a concept design and some concept considerations how such an engine could look like. And one of the big questions is which materials you choose and how you process these materials. For bigger engines, it's sometimes the case that you cannot have it in just one material, so just nickel-based or just copper-based, but you actually need two materials and then combined. You can do that traditionally with copper raw parts that is turned and then some galvanized nickel-based alloy structure on the end. On the other side, there's some development work ongoing to do that in one process or with two additive manufacturing processes combined. So that's it. Thanks a lot for your attention. If you have any questions, I'm here today. That was my last project at AMCM, so if anybody wondering if the part is real, because I've been asked that, it is real. So see you later. Looking forward to your questions. Thanks.
Thank you, Max. We have time for maybe one quick question from the audience if anybody wants to ask one in public, or you can, of course, call Max and ask him in private. I just had a quick one. In terms of materials,
yep.
How well does the materials available to you in AM suit what you want to do at the moment, and how much do you think materials are kind of holding you back?
Yeah, limited. So we're starting with a nickel-based alloy Inconel 718 because it is one of the most mature materials out there, and by chance it was suitable for our process. If we would have more strict requirements in terms of thermal load and mechanical load, possibly it would not be enough anymore. So companies like SpaceX, for example, actively develop alloys themselves because they have even higher requirements and they want to make the parts even better. So for these first steps, we really went for materials that are widely available, firstly in the supply chain, then also in the maturity in the industry, also availability of process parameters in the industry by the OEMs. And that's what we're starting with. For the one engine, we're quite lucky because it fits very well. For others, it might be different, and we also might come to the point where it's not sufficient anymore, and we need to look into new material developments. So limited availability.
Thank you.
Thank you.